In our final application of equilibrium, we're going to look at the context of electrochemistry. And although electrochemical reactions are probably the most complicated reactions that we'll study in this course, we'll find that the principles of thermodynamics and chemical equilibrium that we've developed already will apply equally well to an electrochemistry context as any other. In particular, when studying electrochemistry, we often don't deal with changes in free energy directly, instead opting to study electrical values like voltage and current, and we'll see the emergence of these quantities in the study of electrochemistry in this series of videos. But before we get into the electrical side, let's take a look at redox reactions, which involve the transfer of electrons from one chemical species to another. We want to start off understanding the molecular details of redox reactions before we begin thinking about the broader thermodynamic and equilibrium picture. So there are many reactions that involve the transfer of electrons from one species to another. A good example is the reaction you see at the bottom of this slide. Aqueous copper sulfate reacts with solid zinc metal to form solid copper metal and aqueous zinc sulfate. If we separate the ionic compounds on either side of this reaction, we find that we have Cu2+ on the left and Zn2+ on the right. And it's worth noting that the metals are zinc 0 on the reactant side and copper 0 on the product side. So notice what's happening here. We're going from copper 2+ to copper 0. 2 electrons are being transferred to the copper atom. And we're going from zinc 0 to zinc 2+. 2 electrons are being transferred away from the zinc atom. Transfer of electrons to a species, like we're seeing for the copper 2+ ion in this example, is called reduction. Transfer of electrons from a species, like we're seeing for the zinc 0 going to zinc 2+, is called oxidation. And a good way to remember this is the classic mnemonic Leo says grr. Losing electrons is oxidation. Gaining electrons is reduction. Notice that copper 2+ is gaining 2 electrons in this reaction, while the zinc metal is losing 2 electrons. Reduction and oxidation always occur together. This is because free electrons can't just exist out there independently of atoms. So if we give up electrons, that is, if an oxidation is taking place, then those electrons that were surrendered must go somewhere, and wherever they go is an atom or a molecule being reduced. So reduction and oxidation always occur together, and to represent that, we use the term redox reaction for this. RED for reduction and ox for oxidation. Unfortunately, since oxidation and reduction always occur together, there's a little bit of confusing terminology that goes into this. We call the species being reduced the oxidant. ANT comes from French, and it's used as a suffix kind of like ing is used in English, so you can think of the species being reduced as the species that's doing the oxidizing. This is the oxidizing agent, or the oxidant. In the example on the bottom, the reactant that's being reduced, the copper 2+, is the oxidant. It's inheriting 2 electrons from the zinc metal, causing it to be oxidized. On the other hand, the species being oxidized is called the reductant, and this is the species that's doing the reducing. It's the reducing agent. In this case on the bottom of the slide, the zinc metal is the reducing agent or the reductant. We know that because it's losing 2 electrons and donating those 2 electrons to the copper 2+, causing it to be reduced. It's the reducing agent or reductant. Here's a graphic that illustrates this. The reducing agent, which is shown here in green, donates an electron to the oxidizing agent. The reducing agent loses electrons, while the oxidizing agent gains electrons. So the reducing agent becomes oxidized, X is oxidized by Y, while the oxidizing agent gains electrons and Y is reduced by X. And as we just saw, to identify the reductant and oxidant, you want to strip away spectator ions, strip away the sulfate in this case, identify the charges on these ions and the oxidation states from there, which will just be equal to the formal charges in this context. And you want to compare the oxidation state of what's on the reactant side to what's on the product side. So for example, we can identify, since copper goes from 2+ to an oxidation state of 0, that this is a reduction that's occurring, and copper 2+ is the oxidant. And we can also identify that zinc metal is going from zinc 0 to zinc 2 plus, such that zinc metal is the reducing agent and is being oxidized in this process. So being able to separate an ionic compound into its component ions is critical here, because you have to identify the charge on those ions to properly identify the oxidation state and what's the reductant and what's the oxidant. And remember to account for stoichiometry when you're calculating the charge per ion. So let's go through these three examples quickly. KCl is really K plus and Cl minus, and in fact Cl minus is a spectator, right? We see it both in the reactants and in the products in the aqueous phase, and so I'm just going to ignore it essentially. And remember that a solid metal has an oxidation state of 0. So what we're seeing here is that K plus is gaining an electron to go from K with an oxidation state of +1, K plus, to K0, while sodium is surrendering an electron. It's going from sodium 0 to aqueous NaCl, which is really sodium plus. That means that K plus is the oxidizing agent, or the oxidant, as this reaction is written, and Na is the reducing agent, or the reductant. And one thing you should notice about this is that these terms apply only to the reactants, only to the K plus and Na0. In the example on the bottom, we've got two FeCl3s. Each iron within each FeCl3 molecule has a charge of +3, since each chloride has a charge of -1. We've got calcium 0 as a reactant, we've got iron 0 as a product, and calcium 2 plus, since there are two chlorides as a product as well. We can see here again that Fe3 plus is gaining 3 electrons to go from an oxidation state of +3 to an oxidation state of 0, while the calcium metal is losing 2 electrons to go from neutral calcium, calcium 0, to calcium 2 plus. That means that Fe3 plus here is the oxidant, while the calcium metal is the reductant. And you may be noticing a pattern here that the metal with the oxidation state of 0 often acts as a reductant. This is a very common pattern, and elemental metals which have an oxidation state of 0 tend to be pretty good reducing agents or reductants. Finally, an example that illustrates the importance of accounting for stoichiometry is shown at the bottom here. PO4 as an anion has a charge of -3. That means that the 3 magnesiums in Mg3PO42 must individually have charges of +2. So we're going from Mg2 plus on the reactant side to Mg0 on the product side, and we're going from lithium 0 on the reactant side to lithium plus now on the product side. And notice I can conclude that since PO43 minus is really just a spectator, and so each of the 3 lithium atoms within Li3PO4 must have a charge of +1. Since we're going from Mg2 plus to magnesium 0, the magnesium is gaining 2 electrons and serving as the oxidant, and since lithium 0 is going to lithium +1, the lithium is losing an electron and acting as a reductant. So Mg2 plus here is the oxidant, and lithium metal is again the reductant. Here's an example of a redox reaction between aluminum metal and copper 2 plus. The blue solution are aqueous copper 2 plus ions. And probably before you're through general chemistry lab, you'll be well aware of the idea that copper 2 solutions are blue. You can see a little bit of the aluminum foil left over here, but you can also see that there's some brown copper metal forming on the surface of the aluminum metal. Because they're not colored, you can't see the aluminum 3 plus, which is beginning to form in solution. So the overall balanced equation looks something like this. We start with aluminum foil, 2 of those. 2 of those react with 3 copper 2 plus ions, which are aqueous, which are in solution, to form 2 ions of Al3 plus, which are aqueous, and 3 copper metal atoms. We'll come back to this example in future videos in this series. So our big questions about redox reactions are the following. Redox reactions involve electron transfer between 2 reagents, from the reductant to the oxidant. Can we separate the reductant and oxidant in space so that we can somehow push electrons from the reducing agent to the oxidizing agent and convert the chemical energy associated with this spontaneous movement of electrons into electrical energy, into a current? Can we do that conversion? And what are the practical details of a device that accomplishes that conversion? We'll address both of these questions in the very near future. A related question is, if we're going to convert chemical energy in the form of a delta G of reaction into electrical energy in the form of a voltage, how can we calculate the delta G for a redox reaction aside from using delta Gs of formation? Delta G of formation is a perfectly useful method to use even for redox reactions, but it can get a little cumbersome, especially when calculating a voltage is really our goal as opposed to a change in free energy. This raises the question, how can we express delta G for a redox reaction in terms of electrical energy and in terms of a voltage? How does voltage work? And finally, how is delta G related to the equilibrium constant for a redox process, and how can we use this equilibrium constant to our advantage when designing these devices that convert chemical to electrical energy?